My talk is about too much data. It's just a way to explore MySQL in different ways. I hope it's not the state of your head. So my name is Yves Trudeau. I'm a principal architect at Percona since 2009, so almost 10 years, will be 10 years in August. Prior to that, I was with Sun Microsystem, and even before that, MySQL AB for a few months before Sun acquired. I'm a physicist by training, so if you think I'm weird, it's probably normal. I like to understand how things work, so I like to dig when I don't have a model of something. I don't like to be hanging. So why this talk? I have happened to work a lot with customers that were sending a lot of data to MySQL, and they were struggling. So I explored a few things with them, and after that, on my own, just to remove some dark areas in my understanding. And I found that there's a lot that can be done to improve the solution without doing much, so it's pretty interesting. And it's also a nice case study that we can iterate on solutions and have many options. I only have 25 minutes, so I'll keep that a bit simple, but you will still have the time to cover quite a lot. And it allows, I hope, us to discover some internals of MySQL and InnoDB and better understand how to adjust things for maybe your specific workload. Okay, my plan. So first I'll lay out the issue. What are we trying to do? Then I'll present you my benchmark procedure, how I've done, what I've done, and how to test different solutions. And we'll iterate with results, and our investigation will help us to improve things. And after that, I'll present some data compression options to help manage the bulk of the data, and some extra discussions if we have time. So there has been a bit of misunderstanding. That talk could have been 50 minutes, and it's 50, it's 25, so I had some extra material prepared in case. Okay, could you want to switch the page, please? Hey, the issue. So we'll discuss a very simple case. It's a metric-oriented schema. So the columns are typically you need a device ID, something, let's say you're a networking company with devices in the field that have a device ID value, and there's a bunch of metrics for each device. These metrics have a value that you want to recover, and there's a timestamp. So that's really the minimum amount of data, the simplest schema you can have in such a case. The main challenges you have is that you want to be able to insert fast enough while still being able to query it in a decent way. So you need very likely more than 1,000 inserts per second, rows, probably much more than that. And you will need to query by aggregate. You want statistics on the value column by grouping by device ID and metric ID over a time range. So that's very typical. That means given the inserts rate that we have, you will quickly be out of memory. So your data set will be large. So you cannot assume the data will be in the buffer pool at any time, except just at the beginning. There's different approach to metrics. Some will use wide tables with many columns, one per metrics. There's also the narrow approach, the one I presented. Here it's only the narrow one, so don't search multiple columns. There's only the one I showed. Okay, so the benchmarking procedure. So it's a synthetic data set I created. So if you look, I wrote basically a Python script that created 14,000 devices with a random number between 1 and 10 of metric ID. And then the same script generated the values with a correlation with the previous value. So on average, if you do some very simple math, you have 5.5 metrics per device for a total of about 77,000 metrics. That number is not random. There's something in it. I choose to have that one. You will see why later. There's about 5 in my synthetic test. There's about 5,000 iteration of insertions per metric. So every metric ID, every tuple of device ID, metric ID will have 5,000 time values over a period of time. That gives about 285 million rows. So it's just a small test, but you will see it's already pretty interesting. The goal, of course, is to get the fastest possible insert rate with the fastest possible query time. I'll present the query after that. For that, I use a KVM VM in my lab, and I capped it. It cannot do more than 500 I/O combined, so read and writes. The VM has only, whoops, wait a minute, go back. The VM has only 2 gigabytes of RAM, and I used 1 gigabyte for the buffer pool, 2 vCPU, and that's using Percona Server 5725, so a rather recent release. Now the report query, that's a very simple one. I mean, I'm doing an aggregation, but I want average, minimum, maximum, sum, count from metrics for a bunch of devices and 1 metric ID. So it's fairly simple. You will see that even that is very demanding for some solutions. So the metric we're looking at is not the results, it's the execution time. So let's begin our investigation. So probably most of you know that if we insert in primary key order, we get a very good insert rate. You probably find that on the web. If you go with an auto increment PK, so here I defined the ID column as auto increment. So there's very little work to insert one after the other in the B tree. So the B tree, the rows are located with InnoDB in the B tree of the primary key. So you're always inserting to the same page at the bottom. If you look at how the B tree in front of you, bottom right, and the highest values are on that side. So it's very cheap to insert to the primary key. But it's obvious that it will be a disaster for the report query. So you need an index on device ID, metric ID time just to be able to do something with it. So that will be, so I just use that table, I insert the rows from my tool, and I get something like that, which is not really bad. I mean, at the beginning we have 15, 20,000, which is okay. And then it drops over time, and there's likely little wavy features here. Any idea, people, why though it's not a constant? Huh? It's not flushing here. At no time the checkpoint age is high. B3 page splits. So it causes more cache invalidation because of that. So, and it's slower here because at some point the change buffer saturates and starts to do more work. So the maintenance of the secondary index is the cause here of the slowdown. So let's see what that gives. So the query time is disastrous. It's 48 seconds. Simply because, okay, I have an index, but the value is not covered by the index. If I added the value to the index, the time would be good, but then I basically have two tables with the same size. And it required nearly 25,000 read IOPS just to complete that query. Because MySQL found in the index all the rows it needed, but it needed to randomly go get many, many, many pages from the disk, and I'm capped at 500 IOPS. The size, 23 gig. The B3 of the primary key is very compact. It's well filled, but the other one is not randomly ordered, but it's middle ordered, middle inserted, so it's less packed. The two B3s together cause 23 gig. So that's the first iteration. We have a decent insert rate, poor query time. Now, let's see. What if I want to favor the query time? I'll use a primary key that, if I have that data with that primary key, it would be perfect. And I'll insert and see what happened. So that's really the best primary key possible. All the data is local. Let's see what happened. That's a disaster. So at the beginning, the insert time is quite good. But as soon as there's enough rows to go out of the buffer pool, it falls to almost nothing. Because now it reads pages to get them buffer pool to write. So the insert rate slowly goes down and eventually reach 250. I killed the thing here because after 11 hours, it was at far from done. So 67 million rows instead of 280. Was okay in terms of size, but so if I come back here, what if we always make sure what's in the buffer pool, what is required in the buffer pool, is only a small fraction of the table. So I calculated here that it took about 15 minutes to start to fall. So let's do an experiment. I use a script to generate a bunch of partitions, and if you notice, they are supposed to be 15 seconds. Yeah, yes, 900, so 15 minutes, 900 seconds. So it's exactly the same primary key, but now, basically, I'll fill one B3, and when it's almost 1 gig, I switch to a new one. So this one will be flushed to disk. And all the writes will go here, and so on. Here, of course, it's an experiment. You will never use 15 minutes in real production, but I hope you will never use a 2 gigabyte VM to do that kind of work. Okay, so what's the result of that? See, it's pretty good. So when it starts to fall, we switch to the other partition. So it goes back up, fall, switch. So here, the whole thing took about 6 hours. So do you think the query time will be good with such a situation? So if we look, 0.57 seconds. So and only 320 IOPS this time. That's a very good thing. Now the size, it's bigger. It's not bigger. It should have been smaller because we have an index that we don't have. But since the table is mid-inserted, most of the pages, if not all, are not full and far from. I don't have the output here, but every page has about 9K of data, a bit more than half. While in the first case, the B tree of the primary key was filled at 15K to max. You cannot reach 16. There's a cutoff in InnoDB at 15K. So that's pretty interesting here. So this idea, can it really work? I mean, the partition needs to be tuned for the buffer pool size. So if you have a much bigger buffer pool, you can have a much larger partition. And of course, you don't create a partition ahead of time. You can do it on the fly. It's fairly easy. You won't be doing that probably if you have a server with, let's say, 158 gig of buffer pool. It should not be that frequent. There's only one partition that is really used at a given time. So while you will hear very often that, oh, you should not use too much partition with 5.7. 8 is a different story, MySQL 8. Here, since there's only one really active, the one that has been inserted, and maybe a few others for reads, it's not that a big deal to have many, many partitions. You'll have to adjust the file open limit and things like that, but it's not a problem. The maximum is 8,000 partition. I've never seen somebody with 8,000 partition. Maybe you have. And I have seen quite a lot of strange situations. I don't know if that will work correctly, but I mean, if we look at how far that can lead us, 100 gig buffer pool on a server that is decent could lead up to 800 terabytes of data. That's quite significant. So now, that's a lot of data. You don't want to store that uncompressed, especially since we're looking at pages that have a lot of free space in it that will compress very well. So we have to do something to not store pages full of zeros. So the basic options, InnoDB compression. So let's say we try with 8K. It's not too bad. The minimums are at about, what, 9,000? And the max are at 14, approximately. So it's not too bad. The speed is, so the time is, the average is now at around 10. There's a bit, my graph doesn't fully fill the time span, so the average is a bit lower than what it should be. But it's decent. What are the other options we have? Yeah, the query times, 0.79. The size is down to 11.5 gig, down from 21. Now, what if we use ZFS? For one, I know I like ZFS. 20,000 now, and it's rather smooth, actually. It's pretty good. The query time is a bit longer, 0.97, 216 read IOPS. So ZFS has to decompress. I don't know. There's still things I want to understand with ZFS. Why in some operations it's slower? It shouldn't. The size, with InnoDB compression, we were at 11 something. Here with a 9.4. So it's going on the right direction. I just tried for fun to use gzip. So if you use gzip with ZFS without specifying the compression factor, it's -6. So the regular gzip. We're down just a little bit. Not bad. So we're still at maybe if I add the edges at 18,000 rows, given that it's a very tiny setup, it's not bad. So, and it's capped on IOPS and all that. So it's pretty good. The query time is now down at 0.66. Only 192 read IOPS, and the size is 7 gig. So we're at 1/3 of the original size. So it's pretty interesting. And here, the page, the way it works, it's very light on ZFS for the write. Doesn't have to write too much. So, summary. There's one thing I want to cover before that. You realize I use 77,000 metrics, pair device ID metrics, is because every metrics becomes a hot page in the buffer pool where every pair points to one page in the buffer pool where the rows are inserted. I use 77,000 because if you multiply by 16K, it's 1.2 gigabyte. It's bigger than my buffer pool. So I cheated. If you have a large buffer pool, you will not have so much problem, even with that. I go back to the original one. Even with such a schema, let's ignore for the Bepartian. Not be too bad if the number of the tuples you have there, if the number of hot pages that are inserted fits in your buffer pool, you will be pretty okay. So if you have decent log files to support that, it will work just correctly. Actually, I wanted to show a fall, and I had 5,000, 10,000 instead of 14,000, and it never felt really. It was a bit wavier. I unfortunately trashed that instance before saving the graph, so I don't have it. But it's not that bad. So unless you have a very, very large number of metrics to record, just to have enough space in your buffer pool to fit all those pages, because it's not truly a random insertion order. You have hot spots in your buffer pool, pages that are inserted over and over. And once they're full, they're written to disk and they move to the next one. Not full, they're split in two and continue. But so that could work. Even with that, though, even with a larger buffer pool, since you're not inserting at the tail of the B tree, you'll have a lot of free space in your pages, and you should compress data. How much time do I have left? That's not too bad. So go back at the end. So summary, insert rate. So you see that the uncompressed one and the gzip are quite good. Actually, that's quite interesting that the ZFS are higher. There's less I/O to write. So because of the ZFS compression, the way it works with the KVM, the query time. So all those are fairly okay. Keep in mind it's a logarithmic scale, so that one is really off the chart. I had to do that because those were lines. You couldn't see any features. Data set size, so see that from the natural one or the auto increment one, you have the other ones are much, much smaller. So we're talking about a third. Extra discussion, just wanted, but we already covered some of these. Of course, I mean, there's other solutions. I don't intend to tell you that you should insert metrics in InnoDB all the time. Sometimes you already have everything around that, and it's so you have the database. That's the case of most of my customers. They already have the whole setup around MySQL, and they want to put it there. because they don't want to add another database. I'm just showing you that it can work correctly if you have the correct schema. The worst thing you could do is use an increment primary key, because then you're paying a terrible price for the queries. But if you give it enough space for the hot pages, it will work correctly.